Let's look at one last example where we have numbers and variables. In this example, we're simplifying the square root of 108 times m to the 12th power times n to the 9th power. Let's start with the number 108 and factor out the largest perfect square factor, if there is one. So we go through our list of perfect squares and we try to find the largest number from this list that divides evenly into 108. 108 divided by 4 is equal to 27, or 108 is equal to 4 times 27, so 4 is a factor. But let's see if we can find any larger factors. 108 divided by 9 is equal to 12. So 9 is also a factor. 16 does not divide evenly into 108. 25 does not divide evenly, but 36 does. 108 divided by 36 is equal to 3. If we keep going through this list, 36 is the largest perfect square that divides evenly, or is a factor of 108. So we start by writing 108 as the product 36 times 3. And since 36 is a perfect square, we'll be able to take the square root of that to move it outside of the radical. Now for the variables, remember, if the variable has an exponent that's a multiple of 2, then it's a perfect square. So we don't have to do anything to m to the 12th. M to the 12th power is a perfect square. N to the 9th power is not a perfect square because the exponent is not a multiple of 2. So we will factor out one factor of n. That gives us n to the 8th power times n to the 1 power. Remember, 8 plus 1 gives us the original exponent of 9. And n to the 8th power is a perfect square. So we'll take the square root of each of these perfect squares, and those will come outside of the square root, and we will have a factor of 3 and a factor of n left on the inside. Remember, for the number, we just take the square root. The square root of 36 is equal to 6. For the variables, we have to divide the exponent by 2 when we take the square root. So on the outside, we'll have m to the power of 12 divided by 2, or m to the 6th power, and n to the 8 divided by 2, or n to the 4th power. And then we have the square root of 3 times n, the two factors left on the inside. So here we've pulled out all of the perfect square factors from the original expression. And that's what it means to simplify a square root expression. If you prefer to use the alternative method, then we have to use a factor tree to find the prime factors of 108 and write out the products of the variables. Here's a factor tree for 108. So 108 is equal to the product 2 times 2 times 3 times 3 times 3. Here's my 108. Here's my m to the 12th power and my n to the 9th power. Now we identify all the pairs of common factors. You can see we get a pair of 2's and a pair of 3's. So on the outside, after we take the square root, we'll have a single factor of 2 and a single factor of 3. We have 6 pairs of the variable m, so each of these will come out of the square root as a single factor of m. Here's our 6 single factors of m, and we have 4 pairs of the factor n. Each of those will come out as a single factor of n. Here's our 4 single factors of n on the outside. On the inside, we're left with a factor of 3 and a factor of n. And when we simplify this, we get 2 times 3, which is equal to 6, m to the 6th power, and n to the 4th power. And that's exactly the same answer that we got using the first method. Again, either one of these methods will be fine to use as long as you show your work. Let's end this lecture by explaining why we're told to assume that the variables are non-negative in these problems, and what our answers would look like if this were not the case. We basically want to answer the question, is the square root of x squared equal to x? Does the square root cancel the square? First, let's look at what happens when we have a value of x that's non-negative. Remember that non-negative means greater than or equal to 0. So for example, let's use x equal to 3, a positive value. Plugging in x equal to 3 into this expression, we get the square root of 3 squared, and that's equal to the square root of 9. And we know the square root of 9 is equal to 3. Remember, the square root symbol by itself is always the positive or principal square root. And you can see here that we started with x equal positive 3, and we ended with x equal positive 3. So the square root does cancel the square when the input value is positive. Now let's look at what happens if we plug in a negative value of x. This time, let's plug x equals negative 3 into this expression. That gives us the square root of negative 3 squared, and negative 3 squared is negative 3 times negative 3, which is also equal to positive 9. So just as we got in the first case, the positive or principal square root of 9 is equal to positive 3. Notice here, we started with a negative 3 in the first expression, and then we got a positive 3 in the second expression. In this case, the value that we got on the right is equal to the absolute value of the number that we started with. Because if we raise something to the second power, it will always come out positive. That means if we're not told to assume that the variables are greater than or equal to 0, non-negative, we would have to include an absolute value on the variable when we pull it outside of the square root. In all of the problems we'll be doing in this class, we will be assuming that the variables are non-negative, so you won't have to worry about putting the absolute value in your answer. But it is an important point that we should note. This will actually be true for any even root and even power. For example, the fourth root of x to the fourth power is also equal to the absolute value of x. Because if you start with a negative value of x, the fourth power will make it positive, and we lose the negative. This is a property that only holds for even roots. Odd roots will never have an absolute value, because odd powers and odd roots preserve signs. If you start with a negative value with an odd root, you'll end with a negative value.